Hello, everyone. I am Aram Manasselyan from Mathematical Computations team of Wolfram Research. And today with me here is Siria Sadedin from Machine Learning team. During this talk, we will speak about implementation of neural networks in symbolic solutions of differential equations. And here is the outline of the talk. But first, I will speak about main solvers of differential equations in Wolfram language, such as DSolve and nDSolve. Next, I will speak about two interesting approaches from equations to solutions and from solutions to equations. During the next part of the talk, I will speak about the implementation of neural networks method in DSolve. During the second part of the talk, Siria will discuss the generation and training models of neural networks for this purpose. So let's start. I think all of you possibly know that there are two main functions for solving differential equations in Wolfram language, DSolve and nDSolve. These two functions do the same job, solve differential equations, but they are completely different in nature. nDSolve solve differential equations numerically, and its outcome is an interpolating function presented in this example. And here's the plot of this solution. nDSolve is a very powerful function and can solve almost every differential equation, but it works inside some domain, and we must provide initial and boundary conditions together with equations in order to get a solution. Also, all parameters in the equation for the case of nDSolve must be numeric. In contrast to nDSolve, DSolve returns symbolic solution of the differential equation, and its outcome is an analytic expression. Here you can see the solution of same differential equation obtained by DSolve, and again, here is the same plot of the solution. But for the case of DSolve, we can also use symbolic parameters in the equation, as it is demonstrated in this example. Here, A is a symbolic parameter, and as you can see in this case, solution depends on symbolic parameter, and this solution is valid for all values of this symbolic parameter. And in this plot, you can see the solutions of the differential equation for some values of parameter A. Also, I should note here that DSolve can solve differential equations also without any initial or boundary condition. In that case, DSolve returns the general solution of the differential equation, which contains some arbitrary constant parameters, C1, in this example of nonlinear first-order ODE. To summarize this part, I want to say that the nDSolve is much more powerful function than DSolve and can solve more differential equations, but solutions obtained by DSolve are more general, easier to understand, and easier to use. So next question here, how we can determine how powerful is DSolve? And there are two approaches here. First approach can be called from equations to solutions. In this case, we create a benchmark of examples of ordinary differential equations taken from some well-known textbooks and handbooks on differential equations, such as, for example, Kamke, Polyanin, Zaitsev, Murphy, and some other books. As a result, we will get a benchmark of a few thousand examples of differential equations, which in principle should have symbolic solutions, because these are textbook examples. And we can use DSolve to solve all these examples in Wolfram language. And currently, in version 14.3, DSolve can solve almost 94% of these examples. This is a very good number, and it demonstrates that almost all symbolic solution methods presented in the literature are already implemented in DSolve. The other approach can be called from solutions to equations. In this approach, we can generate thousands or even millions of arbitrary functions, which contain arbitrary combinations of some elementary functions, such as trigonometric functions, power functions, inverse trigonometric functions, hyperbolic functions, exponential functions, logarithmic functions, etc. And for each function, we can use known algorithms to generate its own differential equation for which the function will be a solution. And as a result, we will get millions of arbitrary functions and millions of arbitrary differential equations which have symbolic solutions. And again, we can try to use DSolve to solve these examples in Wolfram language to see how many of them can be solved. Of course, in this case, the success rate will be much lower than 94% because these are arbitrary differential equations, and DSolve can solve only several types of differential equations and cannot solve arbitrary differential equations. But in this case, we will get millions of differential equations together with their solutions, and we can use these differential equations and solutions as a training data to train a neural network, which in its turn can be used to try to find solutions for some other differential equations. And I want to announce that in version 15.0, we already have implemented a neural network-based solver to find symbolic solutions of linear and nonlinear first-order differential equations inside DSolve. And DSolve will call this new solving method only if all other solving methods will fail, or DSolve will provide not a good or not a nice solution. What I mean by not a good solution, for example, implicit solutions or solutions which contain unevaluated integrals or inverse functions, or solutions with very large leaf counts. In that case, DSolve will try to find solution using neural network-based methods. And here are some examples. In example 1, we have a linear first-order differential equation which contains only first-order derivative of dependent function f prime x. So this type of equations are easy to solve. We just have to integrate. And as you can see here, the function to be integrated is quite complicated. That is why the outcome of DSolve will have a very large leaf count as it is presented here. This result you will get in version 14.3. But as you can see here, in version 15.0, we get very nice solution, very simple and short solution for this equation obtained using neural networks. And here is the complex plot of the solution. And in example 2, we have a nonlinear first-order differential equation for which DSolve returns really very bad solution in version 14.3. As you can see, we have an implicit solution here which contains solve object, and also there are several unevaluated integrals in this solution. So this is really very bad solution and almost unusable solution. But surprisingly, for this very complicated nonlinear first-order differential equation, we can find really very simple and very nice solution using neural networks method. And again, here is the plot of this solution. And in third example, we again have a nonlinear first-order differential equation for which DSolve fails to find any solution in version 14.3. But in 15.0, again, we have very nice solution presented here. So to summarize this part of the talk, I want to say that in version 15.0, we have implemented this new solving method obtained by neural networks. And this is a very nice improvement for this version. And this method allows us to find, to guess solutions of some linear, nonlinear first-order differential equations without actually solving them. And before I finish my part of the talk, I just want to do one small announcement. After this conference, very soon, a new Wolfram U course, Introduction to Partial Differential Equations, will go live. And during this course, you can learn some basic information about partial differential equations. Also, you will learn about the types of differential equations, PDEs, their solving methods, applications, and also some well-known famous differential equations such as the heat equation, wave equation, Laplace equation, Schrödinger equation, Maxwell's equation, and some others will be discussed during this course. And this is an interactive course with a lot of interesting examples and exercises. And after completion of this course, you will get completion certificate, and it's absolutely free. So you're welcome to join this course. This is all from my side. Thank you very much. Syria, you can continue.
Thank you. Hi. For my part of the presentation, I want to explain how we tackle this problem of training a neural net for first ODE solutions. As was explaining before, we have this new functionality that we can solve ODE using neural networks. And as you may know, mathematics can be explained like a language. So what we try to do is to model or train a model like GPT in language models are trained to do tasks like the language translation and so on. So for our data generation, we generated 1 million of examples of pairs with problems and solutions. And the model to be able to understand math, as for every language model, we need to encode these math expressions into something that the model can understand, like for inputs and outputs. So to do so, we need to transform the human readable problems into machine readable problems. To do that, we use a leaf representation. And here I have some examples on how we convert these expressions into a machine readable problem. So for example, a single number is just expressed as a number. But for example, root square of 5 is represented as the square and followed by the argument. For a bit more complex example, we have 42. X to the power of 5 is represented as the multiplication of 42 times the power of the arguments. In the argument will be X and 5. And so on for example, minus X can be represented by the operation multiplication. And then you have as argument of the multiplication, -1 and X. Here are some examples on how we have a problem, a solution, and the list of tokens that is generated using this leaf representation. So in this case, we have plus, and the argument of plus will be, for plus will be an integer, and the f prime for this case of the problem. As you can see here, -1 is represented here, and the f prime is represented here. And for the solution, we have the sum of x and c1, as you can see here. So in this way, the machine can understand what is the input and is the output, and understand the problem as a language model. But before passing the inputs to the machine learning architecture, we need to convert this token representation into numbers. So you need to also generate a vocabulary and express each token in the problem and solution as a numeric index in the vocabulary. So for example, you generate with this vocabulary a net encoder and net decoder. And for example, the letter X is represented by the number 63 in the vocabulary. And if you want to go back, you only need to pass to the net decoder. Where is the net decoder? Can you see the full screen? Aha, here. You pass the number to the net decoder, and you obtain back the letter that was represented by the 63. So, what kind of model we use? We use just a simple transformer network encoded decoder, as people may use for translation of languages. It can be, for example, English, French, or French, Chinese. These kind of models are used also for language translation, but in our case, we want to translate a problem into a solution. And with these 1 million examples, what we made was creating this encoder-decoder network in Wolfram Language. And as you can see, the loss function will be just a simple cross-entropy loss layer, which compare the tokens generated with the tokens expected in the sequence. And then here I show just a toy example with hundreds of examples being trained. And we just train the neural network with the examples and using 60 training rounds. And this was used in the developing step just to show how, with a bit of examples, just 100, the loss function is going down. So after this, we were able to show that the model was training correctly, and then we we continue with the million example training, and after that you can see how the results are in the examples showed before. Bye. Okay, and this is how we made it. Fortunately, it went very well, and now we have a machine learning model that can solve ordinary differential equations and provide us with better solutions or beautiful solutions, because before there were some examples, as you saw, that was very complicated for the problem, like compared to the machine learning solutions. That's it. Thank you.
We still have some time, so let's go to Q&A session. I can see a few questions here. The first question, is there any chance to use an NN as a method for simplify? Yeah, this is a very nice question. And we are also thinking about this. And I know that this project is in our to-do list. So hopefully very soon we will have such a possibility in Wolfram Language to use neural networks for simplify problems. The second question, can't the ugly solutions be simplified with full simplified to the ones you get with neural networks? Yeah, this is also a good question. During testing, I saw several cases in which neural function provided a nicer solution, but in principle, this solution is quite similar to DSolve solution, and after some simplifies, we get the same solution. But also there are some cases, for example, the case which I just showed, the implicit solution with unevaluated integrals. In that case, simplify and full simplify cannot do anything. Next question. With respect to the transform human readable problems to machine readable problems and the challenge of math notation, did you also think about how to deal with the challenge of multiple synonymous or alternative math symbologies? I think, Sila, this question is for you.
Yeah, we talk about also use the normal way of just separate the problem into tokens and represent it as we usually do it using brackets and so on, but it wasn't going to good results. So at the end, we choose to use this leaf representation, and also the leaf representation helps to in the generation process is it's beneficial to use the leaf representation to randomly choose operators and arguments. So it's beneficial for the generation part and for the representation part.
Okay, here's one more question, I think also for Syria. For your translation of mathematical expressions into machine-readable material, why did you choose your list plus, int, minus, etc. instead of usual Wolfram language expressions?
Yeah, for the transformer network, you need to convert the expressions into something the transformer network can receive, can be used as input of the transformer network. And for that, you need to generate tokens. In case of language models, we use parts of words, or you can even use letter by letter expressions tokens. But in our case, we needed to choose some tokens that represent the mathematical expressions. That's why we generate these tokens and not usual Wolfram language expressions. In the data set, we have all the representations. We have the Wolfram language representation, we have the token representation, and we have also the Wolfram language expression for the solution and the token representation. But for the training, we needed to convert these expressions into tokens to train the transformer.
Okay, thanks. Another question. When DSolve uses the neural network, do you then verify that it is correct by inserting the proposed solution in the differential equation? Yeah, this is also a nice question. Of course, neural networks not always can provide the correct solutions, and in many cases they can provide some wrong solutions like hallucinations. That is why inside DSolve, we always, if we call neural network solver, we always check and try to verify it before presenting for the users. So if DSolve returns a solution, it's a correct solution. And here I can see another question. I didn't see the final error rate after the 1 million training sessions. What was it? Thanks in advance. Yeah, I think this is also for you.
Yes, this error rate was not in the presentation because what I showed was the 100 example training. It's a toy model, but our error rate was around 10% of tokens as a mean error rate. But as we said, every solution before being present by ML DSolve is tested before we provide this solution to the user. So we are sure that the solution is correct and not in between this error rate that I'm saying. But it was 10% of the tokens.
Yeah, I see another question here. If I have a function like gamma 1 plus 1 over x alpha minus beta, delta, etc., can your training system help in some way? To be honest, it's not clear for me what you mean by gamma. It's a gamma function or just a parameter gamma? Because if a function didn't use in training when method cannot help. And I don't think we used gamma function in this training.
But I don't see this is a differential equation. This is another problem.
Yeah, maybe it's a differential equation.
Okay.
Okay, there are parameters, not a gamma function.
Mm-hmm.
Yeah,
but in
anyway,
general,
it's a differential equation. Yeah.
mm-hmm. Our model cannot solve it because it's not trained for solving these kind of problems. But in general, if you are interested into training a model that does this, you only need to generate your data and try it with the pair representation problems and solutions.
Okay, I think we tried to answer to all of the questions. So if no more questions, I think we can stop here.
Mm-hmm.